It's my pleasure to introduce Professor Kibble for this public talk today. Professor T.W.B. Kibble, FRS, is a theoretical physicist from Imperial College, London. His main fields of research are quantum field theory and cosmology. 100 years of fundamental physics, starting with discoveries such as radioactivity and electron, have culminated in a theory which is called the standard model of high energy physics. This theory is now known to be the basis of almost all of known physics except gravity. I would like to stress this sentence. Professor Kibble is one of the chief architects of this theory. An important ingredient that goes into the construction of the electroweak part of the standard model is the idea of spontaneous breakdown of symmetry. This spontaneous breakdown of symmetry is engineered through a mechanism called Higgs-Kibble mechanism. Although Higgs and many others proposed the idea in the context of abelian gauge theory, it was Professor Kibble who extended it to non-abelian gauge theory in the year 1967, 4 years after the papers were written by Higgs and many other people, including Kibble himself. So Professor Kibble extended it to non-abelian gauge theory in 1967, and it is this that Weinberg and Salam used to construct the electroweak theory in 1967. So please remember the dates. So my opinion is these 3 years elapsed after the Higgs mechanism was known, because the non-abelian extension was not known until Professor Kibble did it, and it is quite a non-trivial feat, because that is what is used in the Weinberg-Salam, Glashow-Weinberg-Salam theory based on the SU2 cross U1 non-abelian gauge fields. The symmetry breakdown of the non-abelian gauge theory is a part of the standard model. Now, the Higgs-Kibble mechanism has passed a crucial experimental test. The Higgs boson seems to have been discovered at Large Hadron Collider at CERN. It was announced on the 4th of July, 2012. Further tests will confirm its existence. Professor Kibble has made many other important contributions. His seminal paper on cosmic streams introduced the phenomenon into modern cosmology. And Professor Kibble has won many honors. Fellow of the Royal Society of London, he is a Fellow of the Royal Society of London. He received the Sakurai Prize and many other things which you can easily get by going to internet nowadays. So I will not go through the whole list of his contributions and the various awards of honor which he has won. But this last piece I have to mention. Professor Kibble was born in Madras, which has now become Chennai, and he grew up in the Madras Christian College campus in Tambaram up to the age of 10. His father was a professor of mathematics at the Madras Christian College and taught me there. Actually, I happened to be in Madras Christian College, of course, much after Professor T.W.B. Kibble left, but his father was still a professor, and I have been taught by him. Tomorrow, in fact, the Madras Christian College is felicitating him in the context of their 175th year celebration. Professor Kibble is the grandson of another famous couple who lived here in Chennai, in Madras of those times. Helen Bannerman, who was an author, and William Bannerman, who was an officer in the Indian Medical Service. So Professor Kibble is closely connected to India and especially to Chennai. We salute him for his path-breaking work and thank him for visiting us and talking to us today. Professor Kibble.
Well, thank you very much for that warm introduction. It's a great pleasure to me to be here in my city of my birth, and I also must apologize to those people who were at the talk I gave this morning, because there will be a good deal of overlap between the two. So I hope that you don't get bored with it. This is not working because excuse me just 1 second. I forgot to plug it in. It's coming. This is a sort of talk about quantum field theory, which is a rather complicated subject, of which there are many specialists here. But I'm assuming that I'm talking now to non-specialists primarily, and so I will try to tell you something about this. This doesn't seem to be working, but I can use this. So I want to tell you about how quantum field theory got started, about the early days, and about how gauge theories in particular developed. This is a historical talk about this development. One of the principal aims after the success of quantum electrodynamics, which was the first real quantum field theory describing the interaction of electrons and photons, one of the objects was to go to describe other forces in a similar way. And a major problem in doing that is what's called the boson theorem. So I have to tell you something about what that is. And the Higgs mechanism is the way of getting around that, of solving problems. And that led on to electroweak unification. And I will talk particularly about the work of Henderson, who was one of my own research group. And about recent experimental confirmation of that theory, and about the more recent work that has acquired enormous publicity about the discovery of what is presumed the Higgs boson, or something very like it. And then I'll finish up by talking about the future. Yes.
You please move the microphone to face the other.
Excuse me a second. It's coming. Is that better? Can you hear me now? Not very well.
Maybe not very well.
Closer to your mouth.
No, to the phone.
Should I put it on? The volume? Is that better? I'm sorry if that was a problem. Okay, you can hear me now well enough? Good. Okay. So let me start with this program. I'm afraid that something has gone wrong with the animation, the order here. I don't know quite why, but never mind. Classical physics has got wave fields, things like the electric and magnetic fields. Quantum physics, and of course classical physics also got particles, like electrons. But in quantum physics, these two things are really the same. We were taught by Planck that electromagnetic waves come in packets, in quanta, with an energy proportional to the frequency. You can think of it as a sort of wave packet, as I've drawn here, a finite train of waves. And so this is a quantum or a photon. De Broglie showed that electrons and protons and such like, which are particles, are also waves. So they share in the property of being waves, and they have a similar relation between energy and frequency of the wave. It's also a case that the particles have a spin, an intrinsic angular momentum, which is related to Planck's constant. It's an integral or half-integral multiple of Planck's constant divided by 2 pi. So what was physics like in 1945? Let me start there. We knew about the constituents of atoms, protons, neutrons, electrons. We had very few other particles. We knew about photons. We knew a few other things. There was the positron. This is a famous photograph which showed the existence of a positron for the first time. This is the track of the particle. It's in a magnetic field, and so it's bent. And the fact that it is definitely positively charged is because it's going in this direction. And you know that because it's, the curvature is bigger after it's gone through this metal plate. It's been slowed down. We also knew about so-called muons and the neutrinos, although nobody had seen a neutrino, and hadn't for a long time afterwards. They had been postulated. These are particles that appear in radioactive decay. All of these had spin 1/2, except the photon, which had spin 1 in units of Planck's constant over 2 pi. We knew about 4 kinds of forces between these particles. The most familiar, of course, were the electromagnetic forces, because they are long range, and so are the gravitational ones, but there are 2 others, the strong nuclear force and the weak nuclear force. The strong nuclear force is what binds protons and neutrons together in atomic nuclei, and the weak nuclear force is what appears in radioactive beta decay and is also important in the generation of energy in the sun. This is in order of decreasing strength. The gravitational force on the scale of elementary particles is completely negligible. The force between, the gravitational force between 2 protons is something like 36 orders of magnitude smaller than the electromagnetic force. So it's the other 3 we will be mainly talking about. Quantum electrodynamics was the first successful quantum field theory, and it was developed in the 1930s, but there was a big problem with it. The problem was that the method of calculation involved a power series expansion in terms of this small parameter, the fine structure constant, which is related to the electric charge on the electron, E. And when you calculate the probability of anything in quantum electrodynamics, you get a power series in alpha, actually in alpha squared. And the lowest order term gave excellent results, but of course, if you wanted more accurate results, you'd have to look at the others. And it turns out that the other terms, B and C and so on, were all infinite. And the solution to that problem was one of the great achievements of the immediate post-war period, renormalization theory. It was found independently by three people, Richard Feynman and Julian Schwinger in the United States, and earlier in Japan by Shinichiro Tomonaga. The simplest way to understand what's going on is in terms of Feynman diagrams, which are a lovely pictorial way of representing what happens with elementary particle interactions. So we represent electrons and photons by either straight or wiggly lines. This is an electron. This is the photon, that's called gamma always. And a typical scattering process between two electrons, so collision between two electrons, is thought of as mediated by the exchange of a photon. And this is a diagrammatic representation. It has a very precise mathematical meaning. This, in fact, gives the lowest order result in this power series expansion that I talked about in terms of alpha. And this gives very good answers, but and it involves a factor of alpha squared, essentially because there are two vertices in this diagram. The results give good agreement with experiments, but we need to look at higher order corrections. And higher order corrections come from more complicated diagrams, things like this, which have more photons exchanged in various ways. And it turns out that some of these, for example, gives an infinite answer. Now, an electron can emit and reabsorb virtual photons. This is actually a consequence of the Heisenberg uncertainty principle. It can emit and it can, as it were, borrow the energy to emit a photon, provided it is repaid within a short time by the reabsorption of the photon. And for that reason, when you look at an electron, it isn't really just a bare electron. It also has a cloud of virtual photons around it. And the mass of the electron is not just what you put into the theory in the beginning, the bare mass, but it includes the contribution of this cloud of virtual photons. And the same is true of the charge. It's not necessarily exactly the same. And what these three people showed is that it's possible to collect together all the infinities into so-called renormalization constants. If you write down the relation between m, the physical observed mass, and m0, that involves infinite constants. But rather miraculously, when you express everything when you express any physical result in terms of m and e rather than m0 and e0, you get a finite answer. So it's possible to extract finite answers from measurable quantities by doing this. And this renormalized quantum electrodynamics was a fantastically successful theory. In 1948, a year after Feynman and Schwinger, Dyson showed that these three approaches, although they looked very different, were actually equivalent. And he presented a proof that the theory, the prescription works to all orders in perturbation theory. All these coefficients are finite. And innovative experiments, wonderful experiments on the lamp shift and on the magnetic moment of the electron, showed that the results are very accurate. Why does it work? We really still do not know entirely why it works. I mean, that's a big subject. There are some answers, but they're not very clear. Dyson's proof did have, as he knew at the time, a gap. It didn't really apply to so-called overlapping divergences. The problem with these things is that every time you have a loop, the mathematical expression involves an integral over the momentum that can flow around that loop. And these integrals tend to diverge and give you infinite answers. And that's where Abdus Salam, who founded the group in which I worked at Imperial College, that's where he made his name first by filling in that gap in the proof. That immediately established him as one of the leading players in the field. So what next? Well, after QED's success, people started to look for similar theories of other interactions, strong and weak interactions in particular. And meanwhile, experimentalists had been working very hard and had found dozens of new particles. Instead of looking at cosmic rays and using cloud chambers, they used accelerators and bubble chambers, and it produced pictures like this. They discovered dozens and dozens of new particles. So we had to make some sense of that. And one of the ways of making sense of that was to try to bring some order into this zoo of particles, was to group them into multiplets, things that look rather similar, and find symmetries relating these, approximate symmetries. The first example was isospin. That was a symmetry that was already invented in the 1930s. It relates to the proton and neutron. The proton and neutron, so far as their strong interactions are concerned, are very similar. They have essentially the same strength of interaction. They have the same spin, very nearly the same mass. And so Heisenberg suggested that there could be a symmetry in which you, as it were, rotate a proton into a neutron and vice versa, and give a mathematical description of this idea. It's called isospin because mathematically the description is very similar to that of the relation between two spin states of an electron, spin up and spin down, which can be rotated into one another. This is not a rotation in the isospin case in real space, but in an imaginary space. And this symmetry is obviously approximate because the proton and the neutron are not identical. The proton has a charge and the neutron doesn't. So it's a broken symmetry. Symmetries are described by symmetry groups mathematically. The simplest symmetry of all is this replacing a wave function, say, by a wave function times a phase factor, e to the I alpha. That is a group called U1. Isospin or spin symmetry involves invariance under transformations between two states, and it's called SU2. It represents linear transformations of this kind. With special features that make it called SU2. We now know, of course, that protons and neutrons are not elementary particles, but are composed of more elementary objects, quarks, the up and down quarks. And SU2 is really a symmetry between the up and the down. The proton is composed of two ups and a down, and the neutron of an up and two downs. And we think of this, as I said, as a symmetry between these two. And there is a larger symmetry called SU3, which relates things made up of the three lightest quarks, up, down, and strange. Strange was because a lot of these new particles that people were finding were called strange particles, and that's because they had a strange quark in them and they behaved in different ways. Now, what about gauge theories? Quantum electrodynamics is a gauge theory. What that means is this. In quantum mechanics, we have a symmetry. The wave function can be multiplied by any phase factor, and it doesn't change anything physically. This is a global symmetry. That means that alpha, the parameter here, is independent of space and time. It's just a constant. In quantum electrodynamics, it turns out there is a local symmetry in which you can multiply by a phase factor which is space-time dependent. And you can make that change provided that you make a similar matching transformation to the electromagnetic potentials. That's a very interesting property. And this idea of replacing a global by a local symmetry has been called the gauge principle. And in some sense, it gives a rationale for the existence of the electromagnetic field, because if you didn't have an electromagnetic field, you would not be able to make this change of replacing global by local. It also seems to provide an explanation for the fact that the photon has zero rest mass. And this idea could perhaps be applied elsewhere. There was a lot of interest in, I've said here, but I mean at Imperial College, where I was. Salam, who was the head of our group, the group was founded in 1956 by Abdus Salam. He was convinced from an early stage that a unified theory of all the interactions would be a gauge theory. And my own first involvement was in 1961, when I showed how gravity might be seen as a type of gauge theory, although not an always successful one. And once people started to think about this idea, they developed more extensive gauge theories, larger gauge theories. The first of those was developed by Yang and Mills, which it was a gauge version of the isospin symmetry. In other words, the idea was to replace the global isospin symmetry by a local one, to invent a theory in which you could have a local version of isospin symmetry. And that was written down, as I said, by Yang and Mills. And actually the same theory was written down by a student of Salam's, Ronald Shaw, although he didn't publish it except as a Cambridge University PhD thesis. Ultimately, this has not proved to be the correct theory of strong interactions, but it was nevertheless a very influential development in developing gauge theories in general, for other fields. And because isospin is an approximate symmetry, this symmetry has to be broken in some way. But if you add symmetry breaking terms, then you actually spoil some of the nice properties of gauge theories. So that was not a very attractive possibility. Another problem with strong interactions is that it's very difficult to calculate anything. The problem is that there's no small parameter like there is for electrodynamics. I mentioned the fine structure constant. We calculated in a power series expansion in that. In strong interactions, the corresponding number would be of order 1. And it's because of that, you can't do the same sort of calculations. And so interest began to shift towards weak interactions, especially after it was found that they too could be regarded as due to the exchange of a spin 1 particle like the photon, in this case called the W plus and minus. And so people started to ask, could there be a unified theory of weak and electromagnetic interactions? Let me compare the two. A typical electromagnetic process involves the scattering of a muon, say, with an electron by the exchange of a photon, which I've already mentioned. A typical weak process is the decay of a muon into an electron and a pair of neutrinos, and that can be thought of as mediated by this W minus particle. So these two things look very similar, and one, if this is well described by a gauge theory, quantum electrodynamics, the suggestion is that this should be true. But there are also big differences between the two cases. The photon has 0 rest mass, and that's a consequence of the fact, or represents the fact, that the electromagnetic interaction is long range. On the other hand, the weak interaction is very short range. It's not really felt outside the range of a nucleus, and for that reason, the W particle must have a very large mass, something of the order of 100 times the proton mass. Moreover, the electromagnetic interaction conserves parity. What that means is the world looks exactly the same if you look at it through a mirror than it does if you look at it directly, whereas the weak interactions do not. They have a handedness. So can there be some sort of symmetry relating the photon and the W plus and minus? If so, obviously, it must be a broken symmetry, not an exact symmetry. Now, quite a number of people tried to write down unified models. The first person who wrote a gauge theory of the weak interactions was Julian Schwinger back in 1956, pointing out that you could interpret it as due to the exchange of a W plus and minus particle. And he suggested there might be a unified theory, although he didn't really say how that could be done. A very important development was by Sheldon Glashow in 1961. He proposed a model with a rather larger symmetry group, not just an SU2 symmetry like outer spin, but also an extra phase symmetry, U1 as well. And that means that instead of just 3 gauge bosons, you have a fourth one, not just the gamma and the W plus and W minus, but Z0. And there was an intriguing mechanism, a mixing between the two neutral gauge bosons, Z0 and the photon. And he showed that by doing this, you could get around the parity problem. You could have a theory in which one of the 4 gauge bosons had a parity-conserving interaction, whereas the others did not. Salam and Ward wrote down essentially the same model, very similar model, also based on the same symmetry group, apparently unaware of Glashow's work. But gauge bosons are naturally massless in the simplest form of the theory. They look massless. And in all these models, the masses of the W plus and minus and the Z had to be put in by hand. And unfortunately, as soon as you do that, you spoil the properties of the gauge theory, and in particular, you make a theory which can't be renormalized, the renormalization program doesn't work, and so you have theories that have infinite predictions. So people started to ask, would there be some other way of breaking the symmetry? And that brings in the idea of spontaneous symmetry breaking. So what is spontaneous symmetry breaking? Well, particle physics, I've already mentioned, has many approximate symmetries. Perhaps they're not all fundamental, but they're spontaneously broken. Now, what does that mean? Spontaneous symmetry breaking means that the vacuum state or the ground state of the system, the lowest energy state, doesn't share the symmetries of the underlying theory. That may seem strange at first, but in fact it's a very widely known phenomenon. The simplest example is crystallization. If you think of a round bowl of water on a table, it looks exactly the same from all directions. It has complete rotational symmetry. But when it freezes, the ice crystals pick out special directions and they break the symmetry. It's spontaneous in the sense that you can't predict in advance which direction it will form. You usually wouldn't have enough information to do that. So it's this spontaneous symmetry breaking. And there are lots of examples in condensed matter physics. Ferromagnetism is another. When a ferromagnetic material cools through the Curie point, it will acquire magnetization, which may be in one direction or another. In a superconductor, it's actually the electromagnetic gauge symmetry that is spontaneously broken. But there was a big problem with the idea of extending this to the relativistic theories that we're interested in. And that problem was the Goldstone theorem. So what is the Goldstone theorem? Well, it has to do with things called Nambu-Goldstone bosons. Spontaneous symmetry breaking means that you have degenerate ground states. Think of a case where the ground state is specified by the direction of something. And whatever direction you can rotate these all to, you have the same energy, that it doesn't make any difference physically. Now, if it requires no energy to go from there to there, then very little energy is required to go to a state in which you have a long wavelength oscillation in the direction. And that means that the energy goes to zero as the wavelength goes to infinity, or the wave number goes to zero. And that is the characteristic of a massless excitation. There is no rest mass involved. So the spontaneous symmetry breaking of a continuous symmetry, something with described by a continuous variable, often implies the existence of these spin zero particles. The excitations of the system are massless. And none of these sort of particles have ever been seen. There are no elementary particles which are massless and spinless. And if they were around, they should be easy to see. And this is the Goldstone theorem, the statement that they should exist. Are they inevitable? Well, if they are inevitable, then of course that seems to rule out the idea of spontaneous symmetry breaking in field theory. So among people who were trying to construct gauge theories of weak or strong interactions, and therefore to get around this problem of having broken symmetry, there was a lot of interest in this and a lot of discussion of how you could get around the Goldstone theorem. There were actually counterexamples known in condensed matter physics, in particular in superconductivity. But it was generally believed by field theorists that massless bosons are an absolutely inevitable consequence of spontaneous breaking in a relativistic theory. And when Stephen Weinberg spent a sabbatical year at Imperial College in 1962, he and Abdus Salam developed a proof of this theorem, which they published together with Geoffrey Goldstone. There seemed to be this impasse, and Weinberg commented, "Nothing will come of nothing. Speak again." So I was very interested to find when, in 1964, when a new postdoc arrived at Imperial College, Gerald Goralnik, who was a student of Walter Gilbert in Harvard. And Walter Gilbert had in turn been a student of Salam's. Gilbert incidentally changed after this to go into biology and was later a Nobel Prize winner in a quite different field. Goralnik had already published some ideas about it, which were not completely correct in the end, but pointed us in the right direction. And he and I and another American visitor started working on this problem, and we and others found a solution. And the solution is what's called the Higgs mechanism. The proof of the Goldstone theorem, it turns out, is perfectly correct, but it involves an assumption, which is a very natural assumption in the context of relativistic theory, but actually is not true for gauge theories. And this was discovered by three different people. There were three different papers, all published in Physical Review Letters in the summer and autumn of 1964. The first one by François Angler and Robert Brout from Brussels, the second one by Peter Higgs from Edinburgh, and the third by Goralnik, Hagen, and myself from Imperial College. And all of us proposed essentially the same model. We were all discussing the simplest kind of gauge theory, a U1 gauge theory, a sort of broken version of electrodynamics. And you think of it, of course, we don't want to break the electromagnetic gauge symmetry as such. But to create a broken version of this theory, and it involves introducing a complex scalar field corresponding to charged spin-zero particles. Charge here doesn't mean that it has an electric charge, because, as I said, we don't want to break the electromagnetic gauge symmetry. It's some other symmetry we want to break. Breaking electromagnetic gauge symmetry would actually mean violating the law of conservation of charge, and that's something we don't want to do. But it's the charge corresponding to this symmetry, whatever it may be. I can't go into great detail about this, but it's easy to see general idea. We have a scalar field. This is the simplest model that illustrates this. It was written down most explicitly by Peter Higgs. It involves a scalar field with a rather unusual form of potential energy, in which this is plotted against the real and imaginary parts of the field, and it has a maximum at phi equals 0, and a minimum around a circle of fixed given radius. So phi and its ground state, in its lowest energy state, has a definite magnitude, but its phase could be anything. And that means that the vacuum state in this theory is actually degenerate. You can choose any particular value of the phase, and that gives you a different vacuum state. It means there's a sort of uniform sea of these particles. That's roughly what having a constant value of the field means. And if you look at, take a particular point here, assume the vacuum state is with phi sitting here, then when phi oscillates in magnitude, you're going in and out, and V has a curvature, and that curvature means that that oscillation corresponds to a massive particle. There is a minimum energy associated with that oscillation, whereas the transverse oscillation, or oscillation in the phase, is in the direction where V is flat. And that means that there is no minimum energy to that oscillation. And so these transverse oscillations would have zero mass, apparently. But it turns out that in the gauge theory, by a rather miraculous process, these transverse oscillations combine with the apparently massless gauge bosons to give you a massive gauge boson, and it gives a mass. This is a very intriguing mechanism, but it works. And that led on to the idea of unification. These three papers, as I've said, were published in 1964. They aroused a good deal of skepticism among the physics community, but nothing else. There were essentially no citations in the first 3 years. So it's a remarkable fact that by 1964, this mechanism was in place, and we also knew about Glasshow's model and Salam Ward's model based on SU2 cross U1, which provided a possible unified theory of weak and electromagnetic interactions. But it still took 3 years more to put these two things together and create what is now the electroweak theory. I did further work, which was already mentioned, on the specific application of this mechanism to non-abelian theories in 1967, and I had a lot of discussion with Abdus Salam about that, and I think it certainly helped to revive his interest in the subject. The unified theory of weak and electromagnetic interactions was finally written down by, first of all, by Steven Weinberg, another Physrev letter published in the autumn of '67. This was a unified theory of weak and electromagnetic interactions of leptons, like the electron and the muon. Salam presented what was essentially the same theory, a very, very similar theory, in a series of lectures he gave at Imperial College. He frequently gave a series of research lectures. And he gave such a series of lectures in the autumn of '67. I unfortunately wasn't there. I was in the States at the time, but I've been told about them by Robert Del Burgo, who was there. Salam didn't, in fact, publish anything on it until the following year, probably partly because he was very heavily engaged in building up the International Center for Theoretical Physics in Trieste at the time, and didn't feel he could spare the time for this sort of thing. So let me say just a little bit about the electroweak model. This was essentially the model of Glashow and Salam and Ward with 4 gauge bosons, one of them massless and 3 massive. And the theory starts with massless gauge bosons, apparently, but with 4 scalar fields, 3 of which get eaten in this mechanism. It's the only way to describe it, to give masses to the gauge bosons. And the 4th is left over and is what is now called the Higgs boson. And the Higgs field, with its uniform sea of particles, sometimes called a condensate, gives a mass to everything it interacts with. And this process is rather similar to the refraction of light, for example, in a plasma, an ionized gas, a plasma with free electrons. A photon propagating through such a plasma will be refracted. It will actually be slowed down. It will acquire a mass because of its interaction with the electrons. It effectively acquires a non-zero mass. This is not in any sense a dissipated process. It doesn't lose energy. It still has the same energy, but it is slowed down. And it's a very similar process that is involved with the Higgs. Now, what happened after that? Well, Salam and Weinberg both speculated that their theory would be renormalizable, could be made into a finite theory, but they couldn't prove it. It was a very complicated algebraic problem, and this was finally proved by a young student, 't Hooft, in 1971. Is a real tour de force using methods developed by his supervisor, Tini Veltman, especially a computer algebra program called Schoenship. In 1973, the key prediction of the theory, which was to do with this extra 4th gauge boson, the Z0, the key prediction was that there should be these weak interactions called neutral current interactions mediated by the Z0, and that was confirmed at CERN, and that led in the end to Nobel Prize for Glashow, Salam, and Weinberg in 1979. Ward, unfortunately, was left out, although he had been a collaborator of Salam's on most of Salam's papers on the subject, presumably because of the rule of 3, the idea that a Nobel Science Prize can never be given to more than 3 people. 't Hooft and Veltman gained their Nobel Prize much later. Why it was delayed so long, I don't know, but they got theirs in 1999. In 1983, the W and Z particles were found at CERN, confirming what everyone believed, that this electroweak theory really is the theory of weak interactions. And while this was all going on, a theory of strong interactions was also being developed. That was a completely independent process, which is also gauge theory, quantum chronodynamics, in which the Higgs mechanism is not involved. The problem of constructing a theory consistent with short-range forces is solved in a completely different way, which I can't go into today. So we now have a standard model based on actually three groups, SU3 cross SU2 cross U1. SU3 is the symmetry group related to the strong interactions, and the other two are related to the electroweak interactions. Now, let me say a bit more about the Higgs boson. In the original papers in 1964, the Higgs boson was really a very unimportant and minor feature. The major thing was giving masses to the gauge bosons. The fact that there was a scalar particle left over was a possibly interesting minor feature. But that changed because after 19S were developed, big pieces of apparatus, over a 20-year period, large groups of physicists devoted themselves to designing and building and finally operating these big pieces of apparatus. And they are truly astonishing pieces of engineering as well as of physics. I'd like to give you a picture of one of them. This is the CMS detector, this is actually the CMS detector in the process of being installed, being lowered into position. I will show you it happening, and I think you can get a really good picture of the size of this and its complexity. It was constructed in the main above ground and then lowered into the position of the tunnel. You'll see it in a minute from underneath coming down. These are really magnificent pieces of engineering. The largest pieces of scientific equipment ever constructed, I think. So there it is. And what is done with these is, in a sense, equally impressive. You can't see that very well at the moment, but you will in a minute. This is one particular event, just showing you what an event looks like. The CMS detector, let me just go back for a moment. You can't see all the layers of it at the moment, but there are many layers detecting different aspects, different kinds of particles, and so on. And out of this you get a very complicated picture. The typical event, you've got protons colliding with each other along this beam pipe. They meet and collide and produce lots of particles. Sorry, that wasn't what I meant to do. That's what I meant to do. And this gives you a picture of all the various layers of the detector, and this is one event, and you see it produces hundreds of particles, and they trigger various bits of the detector, and so out of all this complexity you get something like that. And the computer records all of this, but of course this produces an unimaginable amount of data, tens of terabytes of data per second, most of which has to be thrown away. You simply can't record that much. So there are very complex computing problems involved in you're looking for a needle in a haystack. The interesting events are very, very rare. The result is an almost certain discovery of the Higgs, I believe, of some kind. I'll say a little bit more about that in a moment. So let me say a bit more about what this is. Originally, as I've said, the Higgs was there to give mass, the Higgs field was there to give mass to the gauge bosons, the W and Z. But then it became clear it would also give mass to everything else it interacted with, like the electron. It's often loosely said that the Higgs gives mass to everything else, but that's not true. It does give mass to most of the elementary particles, except for the neutrinos, with which it doesn't interact. But protons and neutrons, for example, acquire most of their mass from a quite different mechanism, from the gluons that stick the quarks together inside the proton and neutron. So that's nothing to do with the Higgs mechanism, and moreover, we have no idea where the tiny neutrino masses come from. We know they have masses, but we don't know where they come from. And the Higgs doesn't actually explain the masses it predicts. It just says the mass is proportional to the strength with which the particle interacts with the Higgs. But you don't know what that is. It could be anything. I've just realized that there's one slide which has got itself out of order, but I might as well show you it now. This is just a picture of the LHC. Just to give you an idea of the scale, this is 27 kilometers around. This is Geneva Airport here. This is the foothills of the Jura Mountains. CMS is sitting under one of the foothills of the mountain. Is this really the Higgs we found? Or the people at CERN have found? Well, the evidence that there is a particle with a mass of about 125 GeV that has many of the properties of the Higgs is very strong indeed. There's certainly something there. There's still a lot of work to do in the next few months and years. We know that this is a particle of even spin, but we don't for sure know that it's 0 and not 2, although I think the evidence is pointing towards 0. We know that it decays, roughly speaking, into the expected channels, but we don't entirely know that all the branching ratios are just what they should be. But again, the evidence is strengthening. I personally think it's almost certainly some sort of Higgs. there are other possibilities. There is the possibility of a supersymmetric extension of the standard model, which is quite popular. In that theory, there would be several Higgs particles, of which the one we found would be the lightest. But unfortunately, we haven't found any others yet. And that would be a very exciting possibility, which would explain a number of things, including possibly dark matter. There were initially some hints of possible discrepancies in the branching ratios, but I think they have rather weakened than strengthened. So, have we finished? Is this the end of particle physics? Well, the very clear answer to that is no. There are huge numbers of problems around. The standard model is an immensely successful model. It's one of the most accurately verified models we've ever had. It explains almost every experiment in particle physics with great accuracy, but only almost everything. It does so with a very large number of arbitrary parameters, 20 or more arbitrary parameters, for example, ratios of particle masses or particle coupling strengths, which we can't predict. It's not really a unified model because you have three separate coupling strengths associated with these three groups. There are suggestions that these three might become unified at a much higher energy scale. Now, the mass scale of that we've been talking about is about 100 GeV, but it's possible that you could have a grand unification at a scale of about 10 to the 15 GeV, far, far away from any possible immediate observation. And one of the reasons for favoring supersymmetry is that this grand unification idea works much better in a supersymmetric version of the theory than it does in the standard model. Moreover, the standard model doesn't include gravity. That's an important omission. And for that, we perhaps need string theory or M theory or loop quantum gravity or various other things. So that really brings me to the end of what I want to say. I want to finish by acknowledging my debt to my mentor and inspiration, Abdus Salam. I've always thought it was a stroke of immense good fortune that I was able to join his group just 3 years after it formed at a very exciting time. And it was a very sad loss when he died prematurely in 1996. Thank you.
I'm sure we all thank him for this excellent presentation of the standard model with the Higgs-Kibble mechanism. Now I would request anybody who, I hope Professor Kibble will be willing to answer any questions or comments from the audience. Anybody with questions or comments? Yes? Somebody there?
Excuse me, sir, why is this ruled out that neutrinos cannot be given mass by Higgs?
Well, in this particular theory, there is no interaction between the Higgs and the neutrinos, so they don't acquire mass from the Higgs. It has to be something else.
Any other question? Yes.
So you mentioned one time you work in the gravity as a gauge theory.
Yes.
But gauge transform in gravity is coordinate transformation. But the gauge theory in the normal gauge field is not the coordinate transformation. So can you comment on that distinction?
Well, I mean, the idea of what I did was to try to think of a gauge theory in which the group of transformations is the Poincaré group of translations and Lorentz transformations. You cannot do that in exactly the same way as for other theories. You have to modify the idea. And I mean, it's interesting that you can do that. It isn't fundamentally very helpful in the same sense as for the other interactions, because the theory that you get out is essentially general relativity and is definitely a non-renormalizable theory as it stands.
Any other question? If not, I would just like to add one comment to what he said. You wondered why Tute and Weltman got the prize so late. My guess is, their renormalization was required in order to do the one-loop calculations, which were subjected to experimental test only in the LEP. That was over only in 1998. So from a practical point of view, maybe Nobel Committee decided to give the prize only after that. I don't know.
Okay, yes, you may be right. You may be right.
Any other comment or question? Okay, if not, let us thank Professor Kibble for his experiment.
So sorry, can I just make an announcement for the student participants? So the bus will take you back from here at 8:30 to your respective accommodations if you're staying off-site. And so please be ready after dinner at 8:30. Dinner will be in the same place, in the guest house complex. And speakers, if you can, please let us know in case you need any help in contacting the hotel to arrange your transport back to the hotel. So dinner will be served in the hotel for the speakers.